Okay, thank you for tuning in. So our next speaker is Sergei Chmutov from Ohio State, and he's going to talk about construction of links from Thompson's group.
Okay, thank you very much. Let me share my screen. And, yeah, so I'm going to speak about this topic, relation between Thompson group and links. That is the topic which was promoted by Von Jones for the last several years. And okay, so let's see. All right, so let's go. There you go. Okay, so the Thompson group was introduced in 1965, and its elements are functions, homeomorphism of the interval from 0 to 1, and each such homeomorphism is going to be a piecewise linear continuous function from the interval from 0 to 1 to itself, and it's supposed to satisfy certain conditions. Okay. Can you hear me? Because I have. Hello?
I can hear you.
Okay. All right. Because something happened with my screen there. I do not see it. Maybe it's my problem. All right. Anyway, so that function is supposed to be continuous, and it fixes 0 and fixes 1. Also, it is linear, piecewise linear, so it is like that on the pieces, and the points where it changes the slope, the points where corners are supposed to be dyadic numbers, and dyadic numbers, that is the numbers of the form and reduced fraction 2 divided by 2, k divided by 2 to the power a. So denominator is the power of 2, that means dyadic. So like 2 to the negative 1, so that is this one, and that is going to be denominator 2 squared 4, and the last condition that the derivative, the slope of the graph is supposed to be the power of 2. And once the slope is power of 2, then the images of all these points are going to be also dyadic number. Also the numbers of the same, no, that's too much. The same form. Maybe I will do it like this. It would be better. Okay, and this is like a couple examples of elements of such group. So that is the element A. So it is a function like this one. On the first half of the interval, it has a slope 1/2. On the second one, the slope is 1, the derivative is 1. And on the last quarter of the interval, the slope is 2. So that is a little bit more complicated element is like that. And the group operation is a composition of functions. So all such functions are invertible. The inverse function is also of the same kind, which satisfies those conditions. And if I compose two such functions, it is going to be also the function of the same type. So they form a group. So this is the Thompson group. My goal will be to give a kind of combinatorial description of elements of this Thompson group of such a function, and then explain this construction, John's construction of link from elements for every element of this Thompson group. So that is my plan. And actually, let me go ahead and tell you that this A and B are going to be the generators of the Thompson group. So any such function can be obtained as a composition of these two. So that is one of the theorem. And my information about Thompson group comes from that paper. of Conan, Floyd, and Perry. A very nice paper about the Thompson group, and in particular, I learned from that paper this presentation of the Thompson group. So A and B are going to be generators, and there are only two relations between those. So that is a commutator of those two elements, this one and that one, and another one commutator between those two elements. And that's all the relations, so everything else will be consequence of that. So it looks like a very easy group, just two generators, two relations, but it is a kind of a very weird group, and we will see its relation to the link, to the knot theory. Okay, and now let me go to explain this combinatorial description of elements of such a group. So first of all, for such a function, I can think about it as a map. So there is an interval from 0 to 1, 0 to 1, and I can draw the diagram like that. I will mark those points where the function changes, the derivative changes the linearity, changes the pieces of linearity, and on the image, and just connect the lines here. And I can think about it like a map, linear map, so it is just a stretching or compression of the interval by a power of 2, because derivative is a power of 2. For example, that half of the interval will go to the quarter, so it is compressed by a factor of 2. So that is like identity map between points of those intervals, so they go identically, and that is the stretching by a factor of 2 on the last interval, and similar for B. So basically what I need to know about the elements of this group, I need to know that partition of intervals into those by those dyadic number, partition of this element of the source and partition of the target of my map. And since it is like dyadic number, so basically I have to know whether I will go to the left half of the interval or to the right half of the interval. And then for each of these halves, I go again in halves, either left or right interval, that will be this one. And that's the situation. And I can encode this by a tree, planar rooted tree. So that is like this. This is the source. So it corresponds to the equation of that interval, 0, 1. So that is the root. And then that corresponds to the left branch, left leg of the tree corresponds to the left half of the interval. The right branch here corresponds to the right half of the interval. And you see that right half of the interval is splitting into the two halves again, left and right. So that is the encoding of this. That is this tree encodes that interval here. So I have that entire half on the right, and that is going to be this leg. And then on the left half of this, I have split it into the two. I split it like that. So that is the encoding of such intervals by planar trees. And again, the number of leaves on those trees, that is going to be the number of intervals right here. So the number of points will be one less than the number of leaves. So 2 points here, internal 2 points, that means corresponds to the 3 leaves. Leaves corresponds to the intervals of that. Okay, and I can see, by the way, the number of planar trees with the fixed number of leaves here, that is the famous Catalan number. And there are hundreds of combinatorial interpretation for Catalan numbers. For example, triangulations of polygons and so on. And so I can think about such element of the Thompson group as a transformation of 2 objects like that, 2 Catalan objects. For example, trees, planar, binary planar rooted trees, like this. And that is the trees corresponding to the element B. And again, the source, it is at the bottom, and I have the left half of the interval, it is like goes immediately into here, but the right branch right half of the interval will be split more. It is split again into the quarters, and left quarter it is right here, and the right quarter it will be split again into halves, so it will be the eighths of the length 1/8, and that is corresponds to those smaller tiny intervals right here, and that is the B. So the transformation of A is going to be like that. I suppose to look at the root of the tree and look at the first leg, the leaf edge to the right of that, and just move it to the left. So it becomes like that. So that is the transformation on A. And on the B, again, if I look in from the point of view of the root, that is the root or root leaf, then I should look not at the first leg, but on the second one to the right. And the second one is moved again to the other side, so it becomes this one to the left. So that is the transformation A and B of the trees, and those are the generators of the Thompson group. Okay, now let's see how we can make calculation in this interpretation of Thompson group. Suppose I would like to do that as again A, so I take that leg next to the next right to the rooted tree and move it over through the root to the left. And if I would like to compose it with itself, that function, so figure out what would be A squared, what's I supposed to do? I supposed to look for another leg here, but there is no such a leg. And what should I do in that situation? And let me return back to the graphs of my functions and see what I can do here. So I have that A, so that graph is like this one. And what I'm going to do here, I'm going to introduce one more artificial point at the midpoint right here. So I will split it more into there. So the slope, it goes smoothly through that point, but still it is a redundant point. But if I will mark this point, the map will be exactly the same as A. So it is the same function, so the same element of the Thompson group. But now I have finer splitting of my interval, finer partition of the interval. I basically I did this 1/4, the last 1/4, and split it into the 2 halves here, up to 7/8 and the last 1/8 of that. And once I will do this one, I will have a different tree here. I have not just tree like A, but I have the last part of it. It will be split more, and that is that part of the tree. And here again, it is split again at the image. So I will have like extra caret to that. And so that means that my description, combinatorial description, it is not quite unique. I can add and remove the extra carets, so the carets at the same place at the source tree and at the target. If I will add them, it is going to be encode the same element, the same function. And I can remove that. And if I would allow this to add in that kind of caret to this place, like that, then I can do calculations in the Thompson group. For example, again, if I consider this one, so what would be A? So I'm looking for the first leg from the root on the right and move it to the left. So it became this one. And you can see I have that extra caret here, which I can think of just a leaf vertex here. If it is a leaf vertex, then it is exactly what is A. But now if I would like to perform another A, I would think in that structure of that leaf vertex and see it here. And once I will do it, then from the root, I can see the right legs, and I can move it over there, so it becomes this one. And that is A squared. So A squared is going to be like that. And after this, we can do calculation in the group. For example, we can figure out that element, and it was one of the elements in the relation in the Thompson group. So we can do A first, then B, then A. So from right to left. So, and I will need, you see, I will need that extra carets here. For example, for this one, that whole thing here is the same, so I can suppress it. And then this is A. So that leg is moved to the left and became this one. But that is a vertex. But to do B, actually, I need that more legs here. So I need more carets. And actually, there are two of them. So there was the first caret here, and then there is another caret to the last vertex there. And then to make B, I am supposed to take the second leg from the root, and it goes to be into that position. And A inverse, then this leg, for the A inverse leg from the left, it goes to the right and became this one. So that is the transformation of trees corresponding to this element. And what I can observe that actually it does nothing to the first leaves. It is going to be the same thing here. So it changes those one, flip this one to that one. And if I will do that combination of elements, B inverse first and then A, so B inverse goes from left to right and transforms that leg into this one, and then A transforms this one to that one. And I can see if I would like to compare these two elements, I suppose to add extra caret, and let's do it at the last vertex. And what I can observe that this actually thing changes the first three leaves, but leave the second two intact because I just take extra caret here. So they leave these elements actually acts on the different subset of leaves. The first one acts only on those two leaves, and the second element, this one, acts on the first three leaves. And since they are independent leaves, so these two elements do commute. So that was one of the relations. The commutator is identity function for these two elements. So we can do it like that. But again, the crucial point that when I will do this description, I can put extra caret anyway, but it has to be consistent in all of the trees. So that is going to be the same description, combinatorial description of elements of the Thompson group. So it is going to be like that. And now let's go to to construction, John's construction of links from elements of the Thompson group. So it is that paper, John's paper, which was published in 2017, but actually in arXiv, it was available from 2014. So quite a while ago. And let's see this construction. So first thing, I would slightly think differently about this transformation of trees. What I will do with that source tree like that, I will flip it upside down. So it is going to be actually this one, and stick it into that one. What is important for the Thompson elements, that the number of elements are the same, a number of leaves on these trees are the same. So I can take one of them, flip it upside down, and so it was like that. Yes, I flip it upside down and then stick it to the target tree, one with another. So basically that half, upper half, that is this tree, but the lower half of that picture, it is going to be that tree only flipped upside down. I can think about these graphs which composed of two trees. So there is a like middle line here as an element of the Thompson group. So And I will construct a link diagram from that. And this is the rule for the link diagram, what Jones proposed to do that. So for each triple vertex, so it is a binary tree, there is a triple vertex on those trees. I have something like a left branch and the right branch on the upper tree, on the target tree. But there is a corresponding triple vertex on the source tree, on the bottom tree. And that is going to be the piece of the diagram, so that vertical line will go underneath all the time. So for example, for this one, so I have to replace that one with those fragments like this one, and it will go to the corresponding vertex. That is the corresponding vertex. So that is what happens here. And that is in this example. So that is that additional line which goes from one vertex to another, and that is goes out. So that is the fragment which was in box on the left picture. And I supposed to do it with every triple vertex there. So just resolve it like this one. And once we do that resolution, it looks like well, I can do rider master 2 moves, and I can move, actually it is like behind everything. So instead of doing that, I can do it like this one. So it seems I will get always a trivial situation, but that is not quite. The point is that this structure might, that strand might go to the right subtree, that to the left subtree. So moving it is like moving over itself, and which does nothing. However, for EA, again, that link, so that is the procedure to constructing the link. So that is L. To construct, maybe I will write it down, L here. Okay, L. So this construction of a link, it for A, it produces a trivial knot like that. But let's look for the more example of this construction. For example, like that, if I do this element of the Thompson group like that, so then again, as trees, it is going to be like that. That is the target tree here upstairs, and the downstairs, it is the source trees. And I'm supposed to get to do the same thing here. So let's take this vertex. So it is going to be that arc, and it corresponds to where it is, this one. So this arc corresponds to that one, and then there is a middle which will go to corresponding vertex at the lower tree. So that is going to be that arc here, and it will be the similar way into there. And then it goes out, goes this way, that one, and that is how it works. So that is the construction. So the link diagram which obtained it is quite tricky here, but we can see. Actually, we can pull. You can observe that there is like a kink here, which I can pull it. It is always over, so I can pull it to the right and then untwist it. And also there is that kink here, which I can untwist, so it will go out. And what it will be maybe I will trace that with red. So, oh yes, and I forgot to say that once I will do this, maybe it is on the previous slide. Once I will do that one, so there is a roots here and there, and I'm supposed to close up the roots as I usually did for the braid group. So just a closure between those roots to make it like a closed link, not a long link, but the closed one. So that closure is going to be right here. And now let me just trace it with red to see it where it will be. So it is going to be, and again I untwist that kink here, and then it is going to be straight because the second one also will be pulled out, and that corresponds to this one. So what I will get the hop link. So just two circles linked together as a Hopf link. Now, if I consider a slightly different element like that, so it will be different trees, and the construction, it is going to be more sort of more complicated, but again, I can pull this arc, pull it off to the right, and that arc to the left, and what you can see a trefoil actually. So that element corresponds to trefoil. And by the way, that gives me such a parameter, such an invariant of links or graphs, what is going to be the minimal number of leaves to represent a given node. For example, for trefoil, it is 5, and 5 is the minimal. That is the Thompson index. I will call it Thompson index. So the Thompson index for trefoil would be 5. For Hopf link, it seems also 5, but I'm not quite sure. It depends on. I'm not quite sure that it is 5, but it seems it is 5. Okay, so that is the construction of the link, and now the Jones theorem. Jones explains this construction in more details in later on at the preprint in 2018, but published in 2019. So the theorem, as we saw it already many times in the talk on this conference, that actually any link can be obtained in that form. So for any link diagram, there is an element in the Thompson group is F, such that the link corresponding to that element is isotopic, so related by the Reidemaster moves to that one. So any link can be realized by a Thompson group. And again, this is the rule, just a reminder, the rule for the construction, Jones construction of that. And by the way, one more remark is here, that if I have an element of the Thompson group and construct a link from that, then I can take the inverse of that element, consider a different element, inverse element to this one, and construct the link from that. What I will obtain is the mirror image of that of the original one. So the mirror image of that one is going to be this link. So the mirror image on the level of the Thompson group, it is just taking an inverse element. And I had, last summer, I had a group of students who worked with the Thompson group, and they did some programs, so that is the programs are available to there. So Dennis Sweeney was one of them. And this is a diagram which obtained by computer, by those computer stuff for the Borromean ring. So this is a Borromean ring here, and he found several of the diagrams. And one more thing about these diagrams and that pictures. So at the beginning, when I started this project last summer with my students, it reminds me, that construction reminds me the grid diagram. And the grid diagram, only in the grid diagram, it seems like a vertical line always in front of the horizontal string. Here it is behind, but that is not a big difference. I propose to look for the grid diagram to looking for that. And my major goal was to looking for the sort of Markov theorem, whether I can describe the moves on the Thompson elements to get the same link. So we didn't succeed this. This is still an open question. What is going to be the analog of the Markov theorem? What are the moves on the elements of the Thompson group or on these trees, which produces the same link? But anyway, so we did, Dennis did the programming and find a lot of those, and that is the picture like a grid diagram for the Borromean ring. And he found it like a kind of 64 probably of those diagrams. That is only 2 of those diagrams, 2 elements of the Thompson group, which gives me Borromean ring. And we can see so that horizontal piece, it is corresponds to this to the triple vertex of the original tree. Original tree was, if it was a triple vertex here, that corresponds to that one, and then I replace it by horizontal pieces like those. Okay, and that was the middle line here. So that was like the leaves of this tree: 1, 2, 3, 4, 5, 6, 7, 8, 9. So the Thompson index is 9. And one of the things we were trying to find the Borromean, the smallest Thompson index, but it seems we didn't actually do all of this. So there is a 9, but maybe it is smaller for the Borromean ring. Okay, and we will return more to that. So the Thompson index definitely greater than the greater or equal to the arc index, and we saw last week we heard a talk about the arc index on the diagram. So the Thompson index is definitely not smaller. Okay, right. And now I'm going to explain the proof of the Thompson algorithm and the proof proof of the Jones theorem, and it is algorithmic proof. So he started from the arbitrary link diagram and transformed it to the diagram of the Thompson element. And it goes through what is called the Tate graph. The Tate graph is related to the checkerboard coloring of the link diagram. Suppose I have a link diagram, say that one. And now I will do check coloring. So I will color this one black. So that is going to be this region here. Then that is going to be that region, this region, that region, this region, and so on. So there is a black region and white region. Then I will put a dot, a vertex on each black region. Actually, if it comes from the Thompson group, then there is that middle line which intersect actually all of the black regions, and I can put that like x-axis. And I can choose the dots, the vertices of Tate graph on this x-axis. And then I connect two vertices connect by an edge through the crossing. So they suppose if the region share a crossing on the diagram, then I connect it by an edge, So I will get the graph right here. And that is the Tate graph, the graph of checkerboard coloring. So again, the vertices corresponds to the black regions, and there are edges here. And moreover, it is signed. We have sign, and sign will be a convention for the sign. It is like that. So if I take like overcrossing strand and rotate it along the black region, rotate it clockwise to get undercrossing, then it is going to be plus. And if I rotate overcrossing, rotate it counterclockwise, I will put minus here. It is slightly different from the Kaufman bracket, just opposite to the Kaufman bracket. So I guess this is like a B crossing, that is like A crossing in the Kaufman's notation, but anyway. So that is the Tate graph. So the Tate graph, it is like that, and it encodes actually the diagram. Now I would say that the signed graph, Tate graph, is in the Thompson position if all the vertices on the x-axis, and we can always do it on the x-axis, then all positive edges, the edges with pluses, are in the upper half plane, and all minuses in the lower half plane here. And also, at each half plane, the edges form a tree. So for example, if I consider upper half plane tree rooted at the left vertex, and it is always can be directed from left to right. So there is only one vertex for each vertex. There is only one vertex to the left of it connected to that, and the similar tree on the lower half plane. So, and if my graph, planar graph, signed graph, the Tate graph is in that position, so then it corresponds to the Thompson element. So the idea John's idea of the proving of that theorem, like Alexander type theorem, is to take arbitrary Tate graph and move Rademacher move to put it in that position, into the Thompson position, which satisfies those conditions here. And that was the idea. For example, if you take this Hopf-Link like that, there are two minuses here, then we can move it to the Thompson position. And there are several steps here. So the first step is going to be we deform all vertices to the x-axis to make it on the horizontal axis. So that is a similar what was in Colin Adams' talk, the first talk on this workshop, when he put all crossings. So that corresponds, the region corresponds, the edges corresponds to the crossing, but we put all the vertices on the same line, horizontal line. So that was the step one. So when I will move these vertices to make it at the same horizontal level, it might happen that some edges crosses that x-axis. And if they crosses the x-axis, I can actually put extra two vertices on this graph with the Rademacher 2 moves. And that is how it looks on on the node diagram. So the edges corresponds again to the black region. So there is a piece of that which goes here and piece of that goes there, and there is a crossing plus or minus here. So there is a crossing on corresponding to that edge. So if it goes like that, then I can move, make a Rademacher move for these two things here for that region and make it like that. And if I will do this, so I will get like a 2 extra black region in my checkerboard coloring, so 2 extra vertices on the Tate graph, and I can do it so that the sign will be like that. If that was plus or minus, then output also plus or minus, and it is plus or minus here, but the middle one will be minus plus. So I can do underneath or overneath that second Rademacher move. So that is the another one. And after that, all vertices, after that step, all vertices will be on the x-axis, and all edges will be either like arcs of a circles, either at the lower half plane or the upper half plane. So it is all satisfied for that diagram, so I do not need to do anything for that particular diagram right here. But then we will have like a next step will be to correct the sign. So if I have a wrong sign, if I have like an edge at the lower half plane and it is positive, at the lower half plane it's supposed to be negative. That was the definition of that. At the lower half plane, it has to be negative. At the upper half plane, it has to be positive. Okay, and that is what step 3 is taken care of. So I will have like that. If I have positive at the bottom, then doing Rademacher 2, I can make it like that, and another Rademacher 2 will make it negatives here. And it's introduced positive at the upper half plane. And similarly, for if I have the minus negative edge at the upper half plane, the 2 Rademacher moves will change it to positive. And that is how it looks on the diagram. So this negative edge corresponds to that crossing here, and that is a negative crossing. And then I will do Rademacher 2, and that between these two branches like that. And then another Rademacher 2 for this one, and it will turn it positive. So now everything is positive, but the, I have more vertices on the Tate graph. So that is how it works. Now, the next thing I have to satisfy that last condition for the Thompson position. I need to correct the direction with the edges from the left. Suppose there is no edges here to the left between this from that vertex. And for everyone except the leftmost vertex, it has to be the edge from the left. Then I can do just that rider master to move between that corresponding branches here, and it will introduce like two more edges. One of them will be plus, one of them will be minus. And after that, I always have the left from the left. I always have the right sign, positive on the upper half plane, negative on the lower half plane. And the last step of the algorithm will be, what if I will have like multiple edges to the left, not just single one, but several of those, two, for example. That is the most tricky thing here. Then I can do those rider master moves, and that is how the state graph will be transformed. And the rider master moves look like that. So if I will do between these two, rider master 2, so that is going to be a top of it, that is underneath. Then I will do rider master 1, so create a sort of little kink here, like that. And then another rider master 2 here. So it will be this one. But and after that it will be just in the Thompson position, so it will be in position. So that basically is the end of the proof of that Alexander theorem. But the only thing which I will like to stress is that this algorithm is highly inefficient. So it is an awful algorithm, and it is indeed very, very hard to run, because you see I create just from a single vertex, that is the black region. I have a 1, 2, 3, 4 vertices instead of 1, so it will like jumps by 4 for that. And indeed it is really hard, and I spent actually a couple of days just to do that very simplest example of the Hopf-link. So if I will do that Hopf-link, which I showed at the beginning, and the first steps satisfied first couple of steps. So I have like upper h, and that is negative h. It's supposed to be positive, so I have to correct it. That was step 3 in my algorithm. So the diagram of this Hopf-link is like that big. So it is extremely inefficient. And from my point of view, one of the main things here in that area would be just to find a different algorithm or improve the Jones algorithm to make it more efficient. Not that ugly. And well, it is not very difficult to see that indeed this is a Hopf-link, and I just colored the component of the Hopf-link just to see, to recognize which one is which one, to sort them out. And that is the corresponding element of the Thompson group. So that is a pair of trees which corresponds to this diagram. So it is hard as that one. And there are 24 leaves, and we saw that actually for the Hopf-link we need only 5 leaves, and here there are 24 of those leaves right there. And one thing to improve the Jones algorithm, that is I noticed when I was preparing for this talk, then actually I can do it better in that particular example, almost no expense. That if I will draw this state graph in the different way, if I will put both edges at the lower half plane, so that is the negative and negative edge. If I would draw it into this one, then I do not need that step 2. I do not need to bother with negative edges. Still, there will be no edges to the left from a vertex, but at least all signs will be correct. And if I will do it, I will get, so if I will draw it in that form, then actually I will get a much better diagram of the Hopf-link. So again, that was like that ugly, and that is also ugly, but not at least that much. So it is slightly nicer. So just for for nothing, for drawing better diagram from the beginning. So to moving this negative edges on one side of the push it down to the negative lower half plane, and positive to the upper half plane for the edges, I will do it like that. And the Thompson, that the element of the Thompson element is going to be corresponding to that beta one. It is this one, and essentially it is basically only that part of that. There is only eight leaves, so it is like 1/3 of the original ugly diagram. So that is a kind of an improvement of the Thompson, of the Jones algorithm, and I think that again, this is going to be one of the main topic of the research, possible research. For that is to construct a kind of efficient algorithm to do that. And I do not have actually any idea except that little one which I just showed. It have to improve the Jones algorithm. Probably the different algorithm would be more desirable in this thing. Then another possibility is to do that. It is going to be to figure out for the first nodes in the table to calculate the Thompson index. What would be the Thompson index? And in particular, I would be glad to know, are there any bounds for the Thompson index if I will do this little t for the Thompson index? Is there something like what we have for the arc index? If there is a crossing number plus some constant, 3, 2, whatever that constant might be, universal constant which would describe the restriction of the Thompson index. So these are kind of direction for future research in future, and I'm going to do it with my undergraduate research program. So this is like an URL for this program. That is where it was written, that program with Boromir ring and the other Thompson elements by students, and I'm going to continue it this year. I will start just in about a week to that, and I would like to work on these problems there. However, if someone else would be like to work on this, I will be very glad, and I will very appreciate very much if you will keep me informed at any progress with that one. And our progress again will be reflected on that website. If you would have any progress in those things, it will be there. So, and that's it. So thank you very much for joining me in this talk, and that's the end of the talk. Thank you. All right. So I don't know.
Are there any questions? Feel free to unmute.
Sergei,
Yes.
hello.
Yes,
Morton.
hello. You. Yes.
Is there any special feature about alternating knots and the Thompson diagram? Because the arc index was on the nose for crossing number +2.
Right. So nothing like that was observed so far. So Jones himself didn't observe and didn't say anything like that. And we were looking last summer. We were looking with my student. We didn't observe that, but that is the right question. Thank you for asking it. It is certainly we should keep it in mind. I hope it should be, but maybe it is not that easy. That's what I think. Yeah.
Can I ask one more thing?
Sure.
the business of putting in a line as a special line, can you make any sense of that line possibly as a braid axis? Because it reminds me a little bit of my old threading construction, again, getting a very inefficient algorithm for presenting a knot as a closed braid straight off a diagram. And maybe, I don't know if there's any way that closed braids feature in this or reflect on it at all. As you say, arc index sounds a little bit more like it.
Good point. You know, it seems to me that the analogy with the braid group does not go too far into that. So I cannot tell you whether this line can be interpreted as an analogous of the braid axis. Might be not. You know, one of the big trouble, and actually the Jones himself noticed that, and we faced it last summer when we trying to do like a Markov theorem for the Thompson group. So, except what I mentioned, that the mirror image is an inverse element of the Thompson group, we didn't actually find any reflection of that algebra of the group structure in the topology in knots. Like, you know, in Markov moves, you can do conjugacy classes, and that is the kind of algebraic structure on the group. And we didn't observe anything for the Thompson group like that. So actually the algebraic structure, the group structure is, I hope it is still involved in topology, but the relation to topology is a sort of still mysterious. So there are a lot of open questions here. Yes, but that was a good observation that if you are looking for the analog with the braid group, then might be this extra line should be treated as that one. And you know, it might be this remark might give some hope, some link. We should think about it, about improving the algorithm. So how to improve that, how to do this beta algorithm, the Jones algorithm. I thought that might be if we will consider the knot represented as a closed braid, and then might be easier to transform it to the Thompson element, and that might be lead if we would think about that line as a braid axis, then might be we can do that. I don't know, but so the answer that the short answer that I do not know, but it's a good question. Thank you.
Thank you.
Yeah, sure. All right.
Okay, so if there are no more questions, then thank you, Sergei. Thank you very much for this nice talk, and we will continue tomorrow morning for us or for whoever likes to join at his time with Sang-Yo Lee's lecture. Thank you.
Right. Thank you.
Bye.